All right, so going on with chapter 16, 16.2, looking at systems of charged objects. And so remember, this is all about potential energy. So we want to see the potential energy between objects of charge. So for these systems, we will be looking at interacting charged objects. And as this is all about potential energy, we're going to want to make sure that we include more objects in our system. All right, and also just note, F-grav is almost always negligible. So remember, the electric force is so much stronger than the gravitational force, and we're going to be primarily looking at pretty tiny masses. So it's not something we need to take into account for this. All right, so if we have a system where everything is inside of it and there's nothing in the surroundings, so system, everything, and surroundings, nothing, then that brings us to the energy principle. Well, we know that energy is conserved, so whatever is gained by the system is lost by the surroundings, but if everything is in your system, then we know that any change of kinetic energy in the system plus any change of potential energy is going to be equal to 0, which of course then implies that delta K is equal to minus delta U. All right, so we're going to analyze a particular system using the energy principle. So we're going to have a capacitor. And we've got a positive charge. And it enters in through a little hole, and it goes from position A to position B. We know our field is going in the direction of the negative plate, and it will travel some delta X. Got the electric force here. And we're going to look at it from an energy principle perspective. All right, so the proton's in there and the electric force is doing work on it, which means that it's going to change the kinetic energy. And we know that the change of kinetic energy of this proton plus the change of potential energy of the electric force, so this is the electric potential, so this is the potential for movement, is going to add up to be 0. So when it first comes in, if we just think about this conceptually, it's going to be going a little bit slower, and it's going to have a lot of potential to go faster because you've got this negative side here that's going to want to pull it forward. And as it pulls it forward, it's going to get faster and faster and faster. And as a result, the potential is going to decrease. So it's just like when we drop something, it's got more potential energy up here, and then in this case, dropped all the way to the floor. Okay, so for this particular setup, let's keep new paper. As we just said, the proton's going to accelerate. Also, the force electric is to the right, and delta X is also to the right, so that's another check. So in this case, the change of potential will be positive, if you recall back from last semester. And then because the change in kinetic energy will be positive, and then therefore that implies that the change in potential is negative because they must add up to 0. Okay, so let's go ahead and start calculating things. So the change in potential energy electric is equal to minus, or the negative of the work internal. And work internal is the work done on the proton by the field in the capacitor. So remember, we want to look at potential energies so everything is in our system for this setup. We may eventually have some stuff in the surroundings. All right, so minus internal work, or the negative of internal work, is equal to the negative f of x dx plus f of y dy plus f sub z dz. And this is equal to minus e times e sub x delta x plus e times e sub y delta y plus e sub z delta z. And since we're in a capacitor, and so our electric field is just in x, and our change of distance is also just in x, we can just say that the change in potential energy, let's just make this super easy, is going to be minus e sub x delta x. And so for this particular system, delta x, x final minus x initial is positive, and e sub x is positive, then minus e sub x delta x is negative. So our potential energy is negative, which is just as we suspected. So it's important when you're doing these derivations to check them with a couple of different concepts. So we figured this out at first by looking at the picture. We did the calculations. We got the same thing, and now we're just doing one more check. And again, we're seeing that, physics works. So in this case, delta K, which is equal to minus delta U, is greater than 0. Okay, so let's do an example. We're going to mix it up a little bit, change up the particle signs. So let's find delta U and delta K in a capacitor with the electric field being equal to 5 times 10 to the 4 newtons per coulomb, and our electron this time travels 6.2 millimeters in the capacitor. And all of this is in x. Okay, so we know that the change of potential energy is minus the internal work, and internal work is something we know how to calculate. So the change of potential energy electric is equal to minus 1.6 times 10 to the minus 19 coulombs, 5 times 10 to the 4 newtons per coulomb, times that distance, that displacement, 0.0062 meters, converting millimeters into meters. And so the change of electric potential is equal to 4.96 times 10 to the minus 17. So in other words, our potential was increasing, which then implies that the kinetic energy was slowing it down. Which would make sense if we were looking at the same capacitor setup where we had positive on this side, negative on this side. If we released an electron and then sent it in that direction, it doesn't want to go there. So it's going to slow down and slow down. And at the same time, that potential is going to build and build and build and build as it gets closer to that repulsive force, which is going to want to then fling it in the other direction. So, and the force electric would be in that direction. Okay, so let's do, this is important, so we're going to do some extra examples. All right, so an alpha moves from location A to location B in a region of uniform electric field. And remember, alphas are a particle. I do expect you to be able to get to the mass and get to the charge. Okay, so if we look at a drawing, I'm going to give you a few more values. So positive plate, our field, and then our delta x from A to B. So the field is equal to 368 newtons per coulomb. Delta x is equal to 1.07 centimeters. We want delta U and delta K. And then if we get delta K, what might be fun is if the alpha starts at rest, what is the speed at B? Okay, so it's initially at A, and the final location is B, and VI, which is speed, is equal to 0. Okay. So our change of potential energy is equal to the negative of the internal work, which is equal to minus the charge, which is going to be twice that of the proton, times the electric field in x times the displacement. So this is equal to minus 2 times 1.6 times 10 to the minus 19 coulombs times 368 newtons per coulomb times 1.07 times 10 to the minus 2 meters. And this is equal to minus 1.26 times 10 to the minus 18 joules, which is making sense. We would expect that it would accelerate towards that negative plate. So delta K plus delta U is equal to 0. So delta K is equal to minus delta U, which is equal to plus 1.26 times 10 to the minus 18 joules. Now, we can use this then to go after the velocity, or the speed, not the velocity. We can infer velocity from looking at this diagram. Okay, so our final speed comes from the non-relativistic expression of kinetic energy. So we know that delta K is equal to K final minus K initial, which is equal to 1/2 mv final squared minus 0 because V initial was 0. So V final is the square root of 2 times Kf over m, which is equal to 2 times 1.26 times 10 to the minus 18 joules over 4 times the mass, so 1.7 times 10 to the minus 27 kilograms. And so our final velocity is equal to 1.95 times 10 to the 4 meters per second. And there you go. All right, so moving on, let's look at the potential difference in a uniform field. Because if we're going to make our fields more complicated, we need to learn the basics first. So let's think back to chapter 13 and what we learned about electric fields. And we related electric fields to force. And we're still doing that. So the force is going to be equal to the charge times that electric field. And it doesn't even matter what's causing the field. If you know the field, the cause is irrelevant. So never assume, unless you're told the cause, what the cause is. You can make some educated guesses, but if you don't know, you don't know, and that's fine. What is important is that you have a number for the field. And the nice thing about this is you can just, once you know the field at this location, you can just drop in any charge and solve. So beautiful, simple equation. Two things, multiplication. Now, what would be really convenient is if we could have something like this to get the change in potential energy of a system, kind of a drag and drop approach. So let's see if we can go after this. So drag and drop for electric potential. Okay, so you want to basically get any charge, drop it in, you know the delta U. So delta U equals Q times something. All right, so let's think about this for a little bit. Okay, so if we think back to our capacitor setup and the moving protons, electrons, and alphas, there's a few things that stayed the same. So the capacitor stayed the same, which meant the field stayed the same. Nice thing about capacitor fields is they're constant all the way throughout. There's no change in the field over that distance, so they're a nice start. That field and the path taken. So maybe we could rewrite delta U as a product of Q displacement, and that special something else. All right, so let's kind of look at protons and electrons. They've got opposite charges, but a lot of things are similar, so they're good starting points. So delta U electric is equal to minus E times X, delta X. So we've got plus E here, and then minus E sub X delta X over there. And then if we look at the electron, we have our delta U electric is equal to plus, in this case, because you've got a minus and a minus, they're going to cancel each other out, E times X delta X. And you could rewrite this as minus E times minus E sub X delta X. And we notice that's the same. And this is our delta V, or our change in electric potential. So let's write this out explicitly. So potential difference delta U electric is equal to Q delta V, and delta V is equal to delta U electric over Q. And let me introduce a new unit. So 1 joule over a coulomb is equal to 1 volt. And you've heard of volts. We have batteries with voltage ratings on the back. And so we should note Delta V is equal to minus E sub x, delta x, plus E sub y, delta y, plus E sub z, delta z. And this implies the units of electric field are volts per meter, which I talked about earlier that we would see this, and there it is. And so this can be used interchangeably with newtons per coulomb. All right, so now we can understand what an electron volt is. So if an electron moves through delta V is equal to 1 volt, then you have delta U is equal to E times 1 volt is equal to 1.6 times 10 to the minus 19 coulombs times 1 joule per coulomb is equal to 1.6 times 10 to the minus 19 joules. So now you know what an electron volt is, which I implied last semester we would get to this value. So electron volt is an energy unit, not a potential. Okay, so now that we understand it with a basic path, we can build on this concept and look at non-parallel paths. And we will actually start with that in the next video.